Hello friends, today I'll start with the optical source for optical communications, right? So if you remember in the introduction section, I discussed that for optical communications you require the two sources and the detector. Okay, sources, so the suppose there is a transmitter, here is the TX and the here receiver is required. So for the TX, the transmitter, and for the receiver. So for in case of the transmitter, the electrical signal that will be entered into the transmitter and that will convert into the optical signal before going to the optical fiber, right? So that channel is used as a optical fiber for optical communication. And again, if it come to the receiver side, then optical signal that will be again converted into the electrical signal and the receiver side. So this will be, there will be one detector inside the receiver, and there will be one source, either it is light emitting diode or it is a laser diode that will be inside the transmitter. So full form, the so two kinds of the sources are there normally used for the transmitter, which is used for the conversion between the electrical signal and optical signal. So one is a light emitting diode, another is a laser. The light emitting diode that will be also considered as a LED, right? So there are some disadvantages, advantages for case of the light emitting diode and the laser diode. So for some purpose you have to use the LED, and for some purpose you have to use the laser diode. Normally, if you come to the data rate, if you use the light, when it will go there will be a conversion between the electrical signal or optical signal. The rate will be 100 to 200 megabit per second. And the driver circuit, to drive the LED, we need a one supply or one circuit, so that is called the driver circuit. That is little bit less complex as compared to the laser driver circuit. Mm. And the fabrication cost is also less if you want to design the LED as compared to the laser diode. So what will be the output we should get from the LED, right? So whatever electrical signal is entering into the LED, so the amount, the rate at which the electrical signal is entering, the amount, the same amount we should get after coming from the LED. Okay, so no, there will be nothing, no waste of the signal or during the conversion between electrical signal to optical signal, electrical signal to optical signal, right? So, so what are the motivation? What are the aim for designing the LED? So first is the high radiance output, first emission response time, and the high quantum efficiency. High radius output means, so suppose the optical signal that will be in the form of the optical, right? So how can you measure so there will be radiance and the spectrum region. So the maximum output, maximum radiation should be there, maximum optical intensity should be there, right? So so normally there is a source, there is a source emitting, so it will be like that, high radiance. Okay, so measures optical power radiated into a per unit, so the solid angle per unit area that defines the radiance. So that will be very much high. And the first emission response time, first emission response time, the time required to the transition between the electrical to optical signal, that is called the response time. That will be very fast. If it is taking too much time, then you will not get the exact amount of the electrical signal in the form of the optical signal after the conversion, right? So that's why the response time also will be the very fast. And then the first, high quantum efficiency. Quantum efficiency that defines the how much electrons are injected, and suppose the if the 100 amount of electrons are injected into the device, so those 100 amount of the electron will produce the photon. That means their efficiency will be high. The ratio between the electron injection and the production of the photon, that defines the quantum efficiency, that will be high. If it is less, that means the 100 amount of electrons are injected. From that 100 electrons, only the few amounts of electrons are produced the photon. That means the efficiency is low. We have to maintain the high efficiency. We have to get the high efficiency from the LED. So how the light emitting diode will work? So it is a one kind of the junction only. You can implement the light emitting diode for in a PN junction diode. So here you can see in the PN junction diode there will be a P and a junction. So if it is work under the forward bias, you will get the current. Okay, so for a case of the forward bias, what is to happen? The hole will be repelled from the P and the electron will be repelled from the N side, and the hole will cross the barrier and the electron will cross the barrier. So all the hole will, once it reach to the depletion region, the hole and then it will come go to the N region. The electron also that will go from the N region to P region. So that during that transmission, the electron, there will be recombination of the electron and hole. Okay, so we have to design such a way that the hole will not pass into the N region and the electron will not pass into the P region. So the electron will inject, hole will inject from the P side and electron will inject from the N side. Both will be confined in a some in a region. So there is a depletion region. In depletion region, there will be no concept of the other freak area. So we have to confine the electron and hole inside the depletion region, and there only within a few moments the electron will be recombined, hole will be recombined with the electron, and that will emit the photon. Okay, so here you can see in this cases. So for the first process, we need to apply the more amount of the forward bias. In the left side diagram, you can see the p-n junction, the number of holes are more in the valence band, number of electrons are more in the conduction band. So it will not move. This will not move. It will not apply any bias. So once we apply the forward bias, then electrons start to holes start to move towards the N region, electrons start to move towards the P region. Now, when all are come together, so you can see near the depression regions, holes and electrons are come together. When these are come together, then there will be a chance of the recombination. The electron will get a one vacant seat. Okay, so electron will recombine with the, so electron means electron will go from the upper state to lower state, and the fill, this will fill the vacant state. That process is called as the recombination. So when this process will take place, then there will be a generation of the photon. You can see there will be a generation of the photon. In this way, the LED will work. So the you have to inject the electron and photon in the depletion region. You have to inject the electron and photon, and this should be confined in a one certain region, so that those electron will not go to the P region. Before going to the P region, it should be recombined, and this hole also before going to the N region, this should be recombined with the electron and hole. So this process is also called as the electroluminescence. So we are giving some electrical bias for getting the luminescence, right? So this entire process is called as a luminescence. So this is explained here only. So how can you confine the electron hole in a one region? That can be achieved using the heterojunction. So if you add the more number of the heterojunction, you will get the more efficiency from the LED. So come to the LED structures. How you design the LED, that depends. That totally influence the quantum efficiency, response time, everything. So for that, you first you need to point out some topics like that. So high radiance and the high quantum efficiency. This we told already. These are the parameters you have to measure. You have to get when you want to design the good LED. So in order to achieve the high efficiency and the high radiance power, so there will be a carrier confinement and the optical confinement. Two confinements are there. One is the carrier confinement, another is the optical confinement. Okay, so the carrier confinement means that I already told. So the electron and the hole and the electron both should be come together for recombination. Okay, the electron and hole both should be come together for recombination. So for this process is the carrier confinement. The optical confinement. Optical confinement means suppose when it recombines, when the electron recombines on the hole, there will be generation of the photon. Okay, so that photon should be all the photons. So suppose 100 amount of photons are produced for the 100 amount of electrons. Those 100 amount of photons, they should not be penetrate into the different direction. That all the 100 amount of photons should be confined in a one region, and then only those photon will be come out from the device. This will not go the other side, and due to the some deflectability, those photon can be reabsorbed by the material. This should not happen. So whatever photons you are getting, all the photons should be come out from the device. So this also depends on the structure. If structure is such a way that due to the reflecting index, those photons also can be reabsorbed. This should not be happen. So that's why the two main properties. One is the carrier confinement, another is the optical confinement. These are two more important when you want to design the LED structure. Okay, so if you confine the electron, if you confine the photon, you will get the high efficiency as well as you will get the high radiance power. So for that, if you keep in mind these two things, you can you have to design the LED based on the double heterojunction. Okay, so heterojunction means in the P and N has the two different band gap, there will be a band bending. This is the heterojunction. If it is like that only, that is called as the double heterojunction. Okay, so there will be a three different kinds of the band gap in a double heterojunction. Yes, we can achieve with the Fourier confinement and optical confinement based on the double heterojunction. Okay, so this we have already told what are the parameters you need to remember. Doping concentration is also importance, and the injection intensity, the active layer thickness. These are also some important parameter if you want to design the LED. So there are the two kinds of the LED: the surface emitter LED, and the edge emitter LED. These I will discuss later. Now come to the structure of the LED. So here I told that the double heterojunction LED heterojunction semiconductors are required to design the high radiance and the high efficiency optical light emitting die. So you can see the structure, the two different outside material are the two different metal contacts are there. This is for contact purpose. You need to connect the forward and reverse bias. So you throw this the metal contact. Then the one substrate is required. On top of the substrate you have to design, you have to deposit the other materials, other active materials and guiding material. So n-type gallium arsenide substrate is used here. Then you can see the n-type gallium aluminum arsenide and p-type aluminum gallium arsenide. Here also one extra layer is there for you to build. So suppose if you deposit the metal layer, so metal can penetrate into the active layer. This should not be happen. So there is one layer is added before the metal layer. So that is gallium arsenide layer. So here also substrate is added. Here also one layer is added. Metal contact improvement layer. Okay. So after that, the two guiding layers. So these two layers are used to confine the electron and hole in a one region, right? So this is the entire gallium aluminum arsenide. There is a gallium aluminum arsenide. So these are called as a light guiding or carrier confinement layer. Okay, light guiding and carrier confinement layer. And this there is a middle region, that is the recombination region or active region, you can call as the active region. Here all the recombination will take place. So all the electron and hole will come here. All the electron and hole will come here. Suppose hole will come from this side to this side and electron will come from this side to this side, and here all the electron will be there. So in this layer the band gap will be such a way that once the electron come here, it will not cross this barrier, this interface barrier. Okay, and here also one hole will come to this side, and this hole will not should not cross this barrier. Okay, should not cross this barrier. This also should not cross this barrier. Okay, so in this, maximum amount of electron and hole will be confined here, and from here they will recombine, and from after recombination, so all the photon will be emitted from this recombination region only. So this is the structure, and this is, you can see the band diagram. Band diagram is like that. You can see band diagram is like that. Okay, so here this side is preset. That means the hole will come from this side to hole will come from this side to this side. Now this the interface band gap, you can see this band gap is high band gap, high barrier. Due to that the hole will not move into that area. And here also you can see this is the less band gap, and then the interface band gap. And the electron can easily inject from this side to this side. And this is the high band gap. Electron will not move this side to this side. So electron will confine here, hole will confine here, right? So after that here the recombination will take place and the photon will generate. So in this way you have to maintain the band gap for double heterojunction. This is for the carrier confinement. Now you can see, if you draw the refracting index profile, so you have to design the refracting index. You have to consider the refracting index for material such a way that there will be a what I will optical confinement also. So whenever the photon will produce from this area recombination region, so suppose the photon will produce from this area, photon will produce from this area. So this all the photon will come out from the device. This should not be absorbed by this the surrounding material. This photon should not be absorbed by this surrounding material. Okay, in this way, the reflective index profile is designed such a way that you can see the low reflective index here, the high reflective index in the recombination region. Okay, so here also the these two, and again the less reflective index for other two regions, the gallium arsenide and the gallium arsenide these two regions. If you maintain the reflective index such a way, then the optical confinement is also possible. Okay, so this is about the working principle of the LED structure. In the next class, I will discuss with that. So this whatever thing I discussed, this thing is mentioned here, and you can see the surface emitter, the theory, just diagram I am explaining here. In the surface emitter, you can see the top of the bottom of the substrate. There is a hole. Okay, the substrate should be the transparent, and the center will be transparent. Other side, you can see materialization had been done. Okay, the center is transparent. So the optical connection will be optical fiber will be connected on the bottom of the substrate. So after the substrate, there will be two layer, or the two are the one is the confinement layer, then recombination layer, and then again confinement layer. Okay, and after that confinement, some insulation layer and isolation layer and the materialization layer also would be done. This is for the precaution, so for outside precaution and the contact. So for other purpose it is used. Okay, so that means the surface of the substrate is connected to the optical fiber. Okay, that's why it is called as a surface emitter. Everything is there. Regarding the structure is mentioned here. So what are the materials you are using? The central layer is sandwiched between the two different n-type and the p-type material. One is the n-type on the top side and the p-type is the bottom side. And the optical fiber is the optical emitting region is perpendicular to the fiber axis. Okay, and some active area we have to maintain some active area, and so equal brightness from all sides will get the equal brightness for these cases. Okay, so this is about the surface emitter, and now come to the edge emitter. In case of the edge emitter, you can see, so in case of surface emitter, on the top of the substrate, we have seen that the top of the substrate is used for the emitting the light. Here in this case, the case of the edge emitter, you can see the surface on the edge of the device will be used for emitting the light. So the top surface is the covered by the metal layer. Top and the bottom surface are covered by the metal layer, and the edge of this layer. Okay, the edge of the layer is used for connecting the optical fiber. In this case, you can see that you can easily get all the power photon. Okay, because it is directly coming from the recombination region. The surface, you can see whatever photons are generated, those photons should be transferred through the guiding layer, and it will come through the surface layer and it will come out. But in this the edge emitter, from the recombination region only you can directly get the photon. Okay, there will be no waste of the photon in this edge emitter. But in this case, so you cannot easily couple the optical fiber, as this is the edge is used for the emitting the light. But if you want to consider about the fabrication feasibility, the fabrication is simple for case of the surface emitter, because easily you can couple the optical fiber with the surface of the LED. So it's due to some factor, and based on the applications, or based on the some advantages disadvantages, we can use the surface emitter and edge emitter for different purpose. Okay, so in the coming lecture I will discuss. I will start with the some other what are the materials can be used for the LED structure and some properties of the LED, and then followed by the laser dot. Thank you. Please like, share, and subscribe my channel.